Hi class, it's Mr. Hofstad here with lesson 6, and we're getting into the second part of unit 5, where the first 5 lessons focused strictly on circular motion, uniform circular motion, and all that. Now we're kind of switching over into gravitation, and at first this might seem like a little bit of a weird transition. It might not seem logical to bunch these things together, but as we dig into it, you'll see how closely connected these things are. And we're going to begin our investigation of gravitational force. Well, kind of a deeper investigation than we've done so far, because we have looked at our FGs, right, mass times gravitational constant. We do know, in that sense, gravitational force always down towards the center of the Earth, right? Now we're going to look at it in a bit of a different light, and thinking about it involving circular motion and later fields. So what was first discovered about gravity, right, the first ideas all came out of astronomy and scientists investigating bodies that are in orbit, right, and the understanding of the planets and the sun and our orbits have definitely evolved over time. So before we get into gravitational force, we're going to kind of lay a historical background. It's a very unique lesson, not many history lessons in our physics 20 course, but here's a fun one, so hopefully you enjoy it. These are testable materials, so you should be familiar with these early theories and these different models of planetary orbit. So this first one, right, all of our old Greek and Roman philosophers and astronomers came up with this idea. They're Greek actually, not Roman. The geocentric view, which is still thought to be true by some certain individuals, but we won't get into that here. So many early Greek thinkers believed that the planets and stars revolved around the Earth in perfect circles. We call it geocentric because Earth is the center. Geo means Earth, in the center. So that's our first and earliest understanding of the revolutions of planets. They thought that everything is perfect circles, which we'll find out was wrong, and that the Earth was the center of it all, which when you're sitting on Earth is understandable, right? So when we look out, we see things moving around us, when in fact we're moving as well. So this idea was around for thousands and thousands of years until Ptolemy came around and made some small adjustments. Again, he kept the Earth at the center, so it's more of a 2.0 update on, or a 1.1, 1.2 update rather than a full new version of our orbits, because we still have the Earth at the center, but we are changing something slightly. So he's a Greek philosopher, Ptolemy. He suggested that the planets moved in smaller circles while moving around their big circle orbits around the Earth. So this was an idea about epicycles. So if we're on the Earth, we see planets, right? Those planets are actually making kind of these little spirals, right? These coils around the Earth as they're orbiting. He didn't know what, but he suggested that they were moving in these smaller circles, these smaller orbits, while they continued on their overall large circular trajectory on the Earth. So it's a little bit of a weird one, but if you can remember that Ptolemy kind of introduced this idea of epicycles. That's kind of the key out of Ptolemy's contribution to our history lesson in the evolution of orbits. Next we have Copernicus. So this was a very daring suggestion. He ended up being killed for ever suggesting that the Earth wasn't the center of it all. So his heliocentric, as opposed to geocentric, has the sun in the center. So Copernicus went against everything that his culture and times were believing about the Earth being the center. Now he places the Earth as just another planet in this orbit. So he thought that they're still in perfect circles. You can see, right? It's almost the same as geocentric. We're just switching where the Earth is in it. We still have perfect circles, but now the sun is the center. All right, those are our 3 precursor theories of the orbits. None of them are correct. Then not that long after. So there's a big gap between Ptolemy and this geocentric and epicenter thinking into Copernicus, right? Thousands of years. And so these guys were only a couple hundred years apart, but this was over 1,000 years. And then only 60 years after, Kepler added on to Copernicus's theory and introduced these new ideas of elliptical orbits. So we have Kepler's 3 laws, which are very important. All right, and these are his 3 laws that are still held true today. So Kepler's first law is that planets orbit the sun with elliptical orbits. An ellipse, right, is this kind of squished circle shape. It's not a perfect circle like our 3 other theories suggested, our 3 other views, but instead it's right, kind of stretched out, and the sun isn't really the center of it either. The planets revolve around the sun in the ellipse. The sun is one of its foci. So when you're looking at the geometry of an ellipse, you have 2 foci, F1 and F2, and the sun is taking up this F2 position here. All right, that's his first law, right? Planets revolve in ellipses. The sun isn't at the center of it, but rather at a foci, which is off center slightly. Second law, this one's a little bit hard to visualize, but hopefully we can get what we need out of it, is an idea of equal areas. So this shaded area here is the area made between the path or the arc length of the planet over some period and the radius to the sun. So between the sun and that planet's sweeping trajectory, we can create this area, and it doesn't matter where in its orbit it is. Equal period means equal area of sweep. So this little section here will take just as long as this section here. So if a planet were to start here and end there, that takes time, period capital T, whereas moving from here to here, it will actually take the same time. It's going a much shorter distance, but it is still kind of encapsulating the same area between the sun and its path. So when it's close to the sun, it moves very quickly, right? So in this same set period, we're traveling quite far, right? Quite a long path or arc length. Whereas when we're far from the sun, we're moving much slower, so we're only moving that little bit. But the areas are the same. That area is equal to that area as long as the same period of time is being considered. All right, hopefully that makes sense. It's kind of just an abstract way of looking at it and thinking, but in summary, right, when it's at its farthest point away, it moves slowest, when it's at the closest point, it moves quickest. And these are special astronomy names I wouldn't get too hung up on, but they might come up in some homework questions. You have your aphelion or your perihelion, right? Close to the sun, far from the sun. And finally, we have his third law, which is Kepler's equation, and this is the one that we can actually analyze and use in some calculations to do some problem solving. So the ratio of period squared, right, this capital T, this period squared, divided by radius cubed, so pay attention to our suffix there, sorry, our superscript, our exponent. Period squared over radius cubed is constant for all planets revolving about our sun. This, as long as we're looking at our solar system, this will hold true for every planet. That could actually be true for any solar system or any central mass. So capital R is the average radius of the orbit. So since we're working with ellipses, right, you kind of have to find that average radial length, which will be given to you or you're going to solve for. So it needs to be an average, which is important. Average radius in meters. Period is the time for one complete orbit, right? So the time that it takes for a complete journey around the sun, which for us on the Earth is a year, right? So the orbital speed is a year on Earth. Orbital period, not orbital speed, sorry. And finally, we have Kepler's constant, which is 2.985 times 10 to the negative 19 seconds squared per meter cubed. You don't have to memorize that. You can always just determine that using the period of an orbit squared divided by its average radius cubed. And it will always come up with that constant number, no matter what planet in our solar system we're looking at. So this Kepler constant, it will only work for our system, right? I think that would change as soon as we're looking at another central mass. Only for our solar system. I'll just call it SS. Okay, so this is a nice calculation based question, right? We can work on. This one is given in our data sheet, but we have to remember what the T's and the R's stand for. You might even be given, no, we're not given Kepler's constant. No, but we can solve that pretty easy if we're given the correct period. All right, let's try our example. We have Jupiter. So we're not looking at the Earth, we're looking at Jupiter. So we're going to have to figure out our period. So our standard equation is period squared over r cubed whenever we're looking at orbital speeds and radii. So we're given the average orbital radius or mean orbital radius of 7.78 times 10 to the 11 meters. So we're working with giant numbers here because we're thinking about space and planets, and those are always a little bit bigger than we're used to working with. We know it has a period of 11.9 years. So we'll have to, depending on actually what the question asks, we might be able to stick to years if they cancel out nicely. If an asteroid has an orbit, okay, so this is of Jupiter, RJ, TJ. We're looking at an asteroid in our solar system. So it gives us a period for the asteroid of 1.27 years. We want to find its mean orbital radius. All right, so we will set up our equation straight from our formula sheet. We know that the period squared of Jupiter over the radius cubed of Jupiter is equal to the period squared of the asteroid over the radius cubed of the asteroid. And we're trying to solve for our radius cubed. So to isolate this variable, I'll multiply both sides by r cubed, and I'll do this one out. This is a pretty long isolation. So those will cancel out. We're searching for this guy. So in order to get him by himself on this left-hand side, we're going to want to multiply by the reciprocal, right? Or divide by t squared, multiply by r cubed to both sides. So that would be rj cubed over tj squared. So those will cancel out, bang, 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 and we're left with ra cubed on the left-hand side, and we have t, the period of the asteroid squared, times the mean radius of Jupiter cubed over the period of Jupiter squared. Right, if you want just a shorter, easier way of doing that, we're just multiplying by the reciprocal, right? So we're going to flip this onto that side. That's essentially what we're doing. So let's throw in everything we know. Here we're looking for RA, so we're going to want to take the cube root of that. So RA is equal to the cube root, right, square root, but to the power of 3 of period squared, which in this case is the period of the asteroid, 1.27 squared, times the radius of Jupiter cubed, which was 7.78 times 10 to the 11. That one is cubed, divided by our period of Jupiter, 11.9 years squared. So when we're looking at our units, the years will cancel out, top and bottom. And this is in meters that are cubed, being cube rooted, so we're going to get a radius in meters because the cube root of a cube is just a meter. And this gives us a radius of 1.75 times 10 to the 11 meters. So it's about 7 times closer to the sun than Jupiter. All right. That was our only example. We just have a little last section of notes, kind of setting us up for our next and our 7th lesson, our last one before Maylong. The inverse square law, kind of put forward by Newton. So going back to Newton, after looking at his 3 laws and all of his work done on forces in our 3rd unit, we're going back to him now, and his probably most famous, I would say to the general public, his most famous contribution to the world, his work on gravity, right? The classic apple falling on his head and him coming up with the idea of gravity. Of course, there's much more to it than that. He created calculus and did tons of experiments, but Isaac Newton attempted to explain what Kepler saw and created laws about this motion of the planets and the moons, and he tried to do this in terms of the gravitational force. So by analyzing the motion of the moon around the Earth, he discovered that force of gravity has an inverse square relationship with distance. So going back to everyone's favorite work with proportionality, the force of gravity is proportional to the inverse square of distance, or 1 divided by this mean radius squared. So we'll get much more into this. This is just a little taste test of next lesson. So that's all I got for lesson 6 for you. Good history lesson and some work with Kepler's laws. These are all important. So get an opportunity to work on this homework before moving on to learn more about Newton's laws of gravitation. Alright, see you later, class.